Welcome back to Calculus, Lesson 9, the theorem. We're going to be doing some more theorems for limits as even more. We're not going to be doing too much in this video, only radicals. So, theorem, real limits of radicals. What does the theorem state? It says that if x naught is part of the domain of the nth root of x, for x being a natural number, and n is greater than 1, then the limit as x approaches x naught of a real number, real accumulation point. So the limit of the nth root of x naught as x approaches a real accumulation point is the nth root of the accumulation point x naught. So how do we prove this? Well, here's our proof. Well, this limit, and we're not even going to use any epsilon delta. That's, dumb. I think we already have enough properties. Let's try. The limit as x approaches, well, of course, we know that these n and n through, assuming that x naught is part of the domain, will just cancel out. So we can make this step. And the limit as x approaches, this right here, what is this? Well, if we plug it in, because it's a monomial, we get, the nth root of, we get this. This whole thing is equal to that. So we can actually make this step. This is totally valid step. And by the limits of composition, remember, there's just the converse of that theorem. We just get this, right? And what is this? Well, it depends if n is even or if n is odd. Either this is the limit as x approaches the nth root of x naught of the absolute value of x, which is still going to be the limit of x as x approaches the nth root of x naught, if that's even, or it's just directly the limit of x as x approaches the nth root of x naught. But in other words, we just plug it in since it's an identity function, and we're done. So that's our proof. That is our proof, guys. So, moving on to our next theorem, semi-theorem. We proved monomials, right? In other words, we proved that the limit of as x approaches, the limit of x to the n of as x approaches x naught is x to the x naught to the n. What about if the exponent is not a natural number? What if it's a rational number? We already have radicals. What is a rational number? Well, it's just, a fraction, right? And, well, what is any number to the power of a fraction? Well, do we have the exponent? Do you know how to take, the monomial? We already have the case for monomials. We already have the case for radicals. So let's combine the two. So, the theorem, if x is part of the domain of x to the power of m, then the limit of x to the m as x approaches x naught is equal to x naught to the m, and m is just a rational number. It doesn't have to be whole number, an integer, a natural number, none of that. It is a rational number. And quick note here, this is not proving in any way the case for irrational numbers, or in other words, real numbers as a whole. Unfortunately, that's beyond the scope of this course as it stands, like right now, but it's possible that we'll get to it later on. So, if m is a rational number, then we can express it as a ratio of two integers, where q is not equal to 0, of course. We're going to use the method of proof by exhaustion, which is casework. Case 1, let m be greater than or equal to 0. Actually, we'll just say greater than 0 because the case for equal to 0 is kind of covered. It's just the case of a constant. It's trivial. We'll move on from that. Then we can say that we can set p to be greater than 0 and q to be greater than 0. And we'll just rewrite our limit, rewrite in the form of radical and exponent, and we'll rewrite this as a composition. And we'll use the limits of composition, right? And now we'll use the limits of radicals here to solve this radical and express it as this. And we'll use the limit of monomial to just directly plug this into that, because we already proved, since p is an integer, I should say it's not not an integer, it's a positive integer, so it's a natural number, of course. So this does work. We can use the limit of monomials we already proved to plug it in. We're back at this ratio, this fraction, sorry. And we're over here now, x naught to the power of m. So we proved for case 1, if m is positive, then this works. However, m can be negative, and here is where it gets a bit trickier. Keep this result for case 1 in mind, because we're going to use it for case 2. So we'll let m be less than 0, then we can just say that p is less than 0 and q is greater than 0. Why don't we choose q to be the negative one? Well, if you remember up here, we have that n is a natural number, and it would not make sense to have a radical have a negative index, would it? No. So we're going to do p to be negative. So we're going to do the exact same step here, except this time we're going to compose these two functions. The limit of 1 over x composed with x to the negative p over q. Well, does this make sense? Well, we have, in this case, 1 over x to the negative p over q. And of course, if we have a negative, we just take the reciprocal. So we have x to the q, x to the p over q, which is what we have. So this works. We're composing these two functions. It's an idea. And by the limits of compositions, we're going to just have this right here. And, well, by case 1, by the result we got from case 1, remembering that what is negative p over q? Well, negative p over q is negative m, but since m is less than 0, negative m is positive. And we already proved the case for when it's positive. So by case 1, we're just going to have the limit of 1 over x as x approaches x naught to the negative p over q. It may look like negative p over q is negative, but it's actually a positive number. So by the limits of rational functions, we can just plug this in, and we can just take the reciprocal to remove the negative, and we have x naught to the p over q, and we can also write here x naught to the m, same exact thing. And by exhaustion, we've proven that the limit as x approaches x naught of x, as x approaches, the limit as x is raised to a rational number as x approaches x naught, which is a real accumulation point, we can just plug it in. You may not see this. You may see this because this isn't super useful, but I mean, it's just proving for rational exponents, right? So it's always helpful to have this in mind. Hopefully this helps, and good luck with your calculus class.